Has this brutality ever happened to you? Has a perpendicular force multiplied by a lever arm ever shoved you in the hallway? Have you ever been a victim of torque? At first, torque may seem innocent, like two kids on a seesaw.
As Michelle said earlier, torque represents the amount of force exerted a certain distance away from an axis of rotation. To calculate the value of torque, you multiply the lever arm, which is the distance away from the center of gravity, by the force exerted on the object, and, if the force isn't perpendicular, you multiply by the sine of theta.
As the radius to the center of mass decreases, the torque decreases, since torque and mass have a direct relationship. Conversely, when the radius to the center of mass increases, the torque directly increases.
Whoever exerts the greater torque has control over where the seesaw is headed. I know what you're thinking. What if there is more than two torques operating on a system? This is where some serious net torque comes into play.
Let's take our seesaw example to a smaller scale and take a look.
Here we will add different masses on each end of the equilibrium, changing the force on each end. As you will see, both radius and forces are different, causing an imbalanced net force. This will make the ruler move to whatever side has the greater torque.
With multiple masses acting on each side of the fulcrum, it is difficult to determine which way it will move or act. By adding all the torques on one side of the ruler and all the torques on the other, using the torque equation T equals R times F times sine theta to find the torque of each mass, you have found the total torques on each side of the ruler. To find the net torque, you subtract these total torques. This will show where the ruler will move and how much torque is acting on this move.
By calculating the torque exerted on each side, you can play with the individual values to try to get a net torque of 0 Newton meters, where the system would be at rest or moving without acceleration. If we keep the number of masses on each side of the meter stick the same, and therefore leave force on each side the same, all we are able to adjust is the lever arm. Let's look at a PowerPoint example. Here we have a beam completely balanced on a fulcrum. If we put a 100-gram block 2 meters to the left of the axis of rotation, then the system will move in the counterclockwise or positive direction. Since torque is equal to force times the lever arm, you have to multiply the 100 grams or 0.1 kilograms by 9.8 meters per second squared to get force, then multiply that by 2 meters for a total torque of 1.96 Newton meters. Because this forces the system to move in the counterclockwise direction, it is a positive torque. Now let's see what happens when we add a 200-gram block 1 meter away from the fulcrum on the right side. We still have a positive 1.96 Newton meter torque, but with this new addition we also have a negative torque exerted since the new block is pushing in the clockwise direction. This new torque is equal to 0.2 kilograms times acceleration due to gravity times 1 meter, or 1.96 Newton meters. Again, this value must be negative due to its direction. Since net torque is the sum of these two values and they are equal but opposite, they cancel out, and the system's net torque is 0 Newton meters. Here, the entire system is at rest. If we were to add a third block to the system, this one 100 grams and place 3 meters to the right of the fulcrum, the system would no longer be at rest. While the torque in the counterclockwise direction remains at positive 1.96 Newton meters, the torque in the clockwise direction now adds up to negative 4.9 Newton meters. To calculate the new net torque of the system, we again have to add the torques in both directions, this time yielding a value of negative 2.94 Newton meters. This means net torque is in the clockwise direction and the system is being forced in the negative direction.
Let's take a look at an average day of Mrs. Hart's AP Physics students.
Oh no, it's locked!
I'm not surprised.
What do we do now? How can we make the AP traction if we can't even get through the door? Let's think about this in terms of torque.
If the door was open, the greatest possible torque could be exerted at a perfectly perpendicular angle, 90 degrees.
You may think that pushing the door at an angle will result in a higher torque, but this is not the case. Because of the sine theta part of the torque equation, any angle greater than or less than 90 degrees will lead to a lesser overall value of torque. Since the sine of 90 degrees is 1, the sine of anything other than 90 is less than 1, and therefore decreases the intensity of the force and thus the overall torque.
But if we have an opposing force on the opposite side of the door, say, I don't know, the torque created by Mrs. Hart's rejection, along with our own on our own side, whichever side of the door has the greater amount of torque on it, where net torque resides, is the way the door will move.
Now let's try to open it with the power of torque. Jeez Louise, I forgot the door was locked. Darn! Now back to Emily shoving Laura. You see how torque has a lot of complicated factors, such as force, distance, and angle? Now watch this.
Hey, nerd! Hey!
Hey!
Nerd! Nerd!
No! Wait until I exert an equal and opposite force that allows for Laura to be at equilibrium. What? When I exert an equal and opposite force on Laura, she has a torque of 0 Newton meters, making her at static equilibrium.
I won't fall down. Thanks, Michelle. I think I should pay attention in Mrs. Hart's AP Physics class. I think I learned a valuable lesson.